The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
I really stated everything about discrete coding as clearly as I could in the notes. I stated it again as clearly as I could in class. I stated it again as clearly as I could in making up problems that would illustrate the ideas. And if I talked about it again, it would just be totally repetitive. So at this point, if you want to understand things better, you got to come up with specific questions, and I will be delighted to deal with them. So we want to go on. Oh, there's one other thing I wanted to talk about. We're not having a new problem set out today. I don't think most of you would concentrate on it very well, but we were. I'll tell you what the problems are, which will be due in October 14th. I'll pass it out later. But it's problems 1 through 7. To 7 and the end of lectures 8 to 10. And one other one all the way at the end, problem 26. So 1, 2, 3, 4, 5, 6, 7, and 26. So you can get started on them whenever you choose, and I'll pass out a traditional problem set form next time. Okay, last time we started to talk about the difference between Riemann and Lebesgue integration. Most people tell me this is further into mathematics than I should go. If you agree with them after we spend a week or two on this, please let me know, and I won't torture future students with it. My sense is that in the things we're going to be dealing with for most of the rest of the term, knowing a little bit extra about mathematics is going to save you an awful lot of time worrying about trivial little things that you shouldn't be worrying about. In other words, the great mathematicians of the 19th century who developed, no, I guess it was really the 19th century, but partly the 20th century. These mathematicians were really engineers at heart. The 20th century and the 21st century, mathematics has very much become very separated from physics and applications. But in the 19th century and the early 20th century, mathematicians and physicists were almost the same animals. You could scratch one and you'd find another one there. They were very much interested in dealing with real things. They were like the very best of mathematicians everywhere and the very best of engineers everywhere. They really wanted to make life simpler instead of making life more complicated. One way that many people express it is that mathematicians are lazy. And because they're lazy, they don't want to go through a lot of work, and therefore they feel driven to simplify things. And there's an awful lot of truth in that. And what we're going to learn here, I think, will in fact simplify what you know about Fourier series and Fourier integrals a great deal. Engineers typically don't worry about those things. An awful lot of engineers, and unfortunately even those who write books, often state theorems and leave out the last clause of the theorem. And the last clause of most of those theorems, the only way to make them true is to add the clause, or not, as the case may be, at the end of it. which makes what they state absolutely meaningless, because anything you can add or not, as the case may be, and it becomes true at that point. And the whole question becomes, well, what are those cases under which it's true? That's what we're going to deal with a little bit here. We're going to say just enough so you start to understand these major things that cause problems, and I hope you will get to the point where you don't have to worry about them after that. Okay, well, the first thing we started talking about it last time, we were talking about the difference between Riemann integration and Lebesgue integration. Riemann was a great mathematician, but he came before all of these mathematicians who were following Lebesgue and who started to deal with all of the problems with this classical integration, which started to fall apart throughout most of the 19th century. And what Riemann said, well, split up the axis into equal intervals, then approximate the function within each interval, add up all of those approximate values, and then let this quantization over the time axis become finer and finer and finer, and if you're lucky, you will come to a limit. And you can sort of see when you get to a limit and when you don't get to a limit. If the function is smooth enough and you break it up finely enough, you're going to get a very good approximation. And as you break it up more and more finely, the approximation gets better and better. If the function is very wild, if it jumps around wildly, and we'll look at examples of that later, then this doesn't work. And we'll see why, in fact, this approach does work. Lebesgue said, no, instead of quantizing along this axis, quantize on this axis. So he said, okay, let's start with 0, quantize into epsilon, 2 epsilon, 3 epsilon, and so forth. And you know, everybody, when they talk about epsilon, they're thinking about something small. And they're also thinking about making it smaller and smaller and smaller and hoping that something nice happens. So then what he said is, after you quantize this axis, start to look at how much of the function lies in each one of those little windows. And I've drawn that out here. Mu2 is the amount of the function that lies between 2 epsilon and 3 epsilon. Now the function lies between 2 epsilon and 3 epsilon, starting at this point, which I've labeled T1, going up to this point, which I've labeled T2, on over here. It's not in this interval until we get back to T3. It stays in this interval until T4. And Lebesgue said, okay, let's say that the function is between 2 epsilon and 3 epsilon over a region of size T2 minus T1, which is this size interval, plus T4 minus T3, which is this size interval. And instead of saying size, he said size gets too confusing, so I'll call it measure instead. And that was the beginning of measure theory, essentially. Well, in fact, other people talked about measure before Lebesgue. There were a lot of famous mathematicians who were all involved in doing this. But anyway, that's the basic idea of what measure is concerned with. Now, for this curve here, it's a nice smooth curve, and you can almost see intuitively that you're going to get the same thing looking at it this way or looking at it this way. And in fact, you do. Anyway, what he finally wound up with is, after saying what the measure was on each one of those little slices, how much of the function lay in each one of those intervals, he would just add them all up. He would add up how much of the function was in each slice. He would multiply how much of the function was in a slice by how high the slice was up, and then he'd get an answer. One difference between what he did and what Riemann did was that he always got a lower bound in doing it this way. If he was dealing with a non-negative function, his approximation was always a little less than what the function was, because anything that lay between 2 epsilon and 3 epsilon, he would approximate it as 2 epsilon, which is a little less than numbers between 2 epsilon and 3 epsilon. So this is a lower bound, whereas this is is whatever it happens to be, however you decide to approximate the function there. And there are lots of ways of doing it. Okay, well, I won't prove any of these things. I just want to point them out so that when you get frustrated with this, you can always rely on this, which says that whenever the Riemann integral exists, in other words, whenever the integral that you're used to exists, namely whenever it has meaning, the Lebesgue integral gives you the same value. Okay, in other words, you haven't lost anything by going from Riemann integration to Lebesgue integration. You can only gain, you can't lose. The familiar rules for calculating Riemann integrals also apply for Lebesgue integrals. Okay, you remember what all those rules are. You probably know all of them better even than this fundamental definition of an integral, which is split up the function into tiny little increments, because throughout all of the courses that you've taken, learning about integration, learning about differentiation, learning about all of these things, what you've done for the most part is to go through exercises using these various rules. So you know how to integrate lots of traditional functions. You've memorized what the integral of many of them is. You have many ways of combining them to find out what the integral of many other functions is. If you program a computer to calculate these integrals, the computer can do it both ways. It can either use all the rules to find out what the value of an integral is, or it can chop things up finally and find out that way. And as I've said before, if you think that being able to calculate integrals is what engineering is about, think again. I told you before you could be replaced by a digital computer. It's worse than that. You could be replaced by your handheld Palm, whatever it's called. Okay, you can be replaced by anything. After a while, we're going to wear little things embedded in our body that will tell us when we're sick and things like this. You can be replaced by those things even. Okay, so you really want to learn more than just that. Okay, for some very weird functions, the Lebesgue integral exists, but the Riemann integral doesn't exist. Why do we want to worry about weird functions? I want to tell you two reasons for it. I told you about it last time. One thing is an awful lot of communication theory is concerned with going back and forth between the time domain and the frequency domain. When you talk about things which are straightforward in the time domain, often they become very, very weird in the frequency domain and vice versa. And I'm going to give you a beautiful example of that probably the next class. You can look at it. It is in the appendix, and you'll see this absolutely weird function, which has a perfectly well-defined Fourier transform, and therefore the inverse Fourier transform of this nice-looking thing is absolutely weird. The other reason is even more important. We have to deal with random processes. We have to deal with noise functions, which are continuously varying functions of time. We have to deal with what we transmit, which is continuously varying functions of time. And just like when we were dealing with sources, we said if we want to compress a source, it's not enough to think about what one source sequence is. We have to think about it probabilistically. Namely, we have to model these functions as sample values of what we call a stochastic process or a random process. In other words, when we start talking about that, these functions, which already look complicated, just become sample points in this much bigger space where we're dealing with random processes. Now, when you're dealing with sample points of these random processes, weirdness just crops up as a necessary part of all of this. You can't define a random process which consists of only non-weird things. If you do, you get something that doesn't work very well. It doesn't do much for you. People do that all the time, but you run out of steam with it very, very quickly. Okay, so for both reasons, we have to be able to deal with weird things. The most ideal thing is to be able to deal with weird things and get rid of them without even thinking about them. what's the nice thing about Lebesgue theory? It lets you get rid of all the weirdness without even thinking about it. But in order to understand it to start with, so we get rid of all that weird stuff, we have to understand just a little bit about what it's about to start with. Okay, so that's where we're going. Well, in this picture, let me put the picture back up again. I sort of sloughed over something. For a nice, well-behaved function, it's easy to find out what the measure of a function is, namely what the measure is of the set of values where you're in some tiny little interval. And that's straightforward to do. It's just the sum, or just the sum of a bunch of intervals. But now we come to the clincher, which is we want to be able to deal with weird functions too. And for weird functions, this measure of the set of values of time in which the function is in some tiny little slice here, the measure of that is going to become rather complicated. And therefore, we have to understand how to find the measure of some pretty weird sets. So Lebesgue went on and said, okay, I'll define how to find measure of things. And you know, it's all very intuitive. If you have any real numbers, A and B, if I have two real numbers, I might as well say one of them is less than or equal to the other one. So A is less than or equal to B. I want to include minus infinity and plus infinity here. When we say the set of real numbers, we don't include minus infinity and plus infinity. When we talk about the extended set of real numbers, we do include minus infinity and plus infinity. Here, for the most part, when we're dealing with measure theory, we really want to include minus infinity and plus infinity also because they make things easier to talk about. So what Lebesgue said is, for any interval, the set of points which lie between A and B, and he started out with the open interval, namely the set of points not including A and not including B, but including all the real numbers in between. The measure of that is what we said before, and none of you objected to it. The measure of an interval ought to be the size of the interval, because after all Lebesgue was doing was taking size and putting another name on it, because we all thought of it as being size. So the measure of the interval AB is B minus A. And now, as engineers, we all know that it doesn't really make any difference whether you include A or you don't include A when we're trying to find the size of an interval. So he said, okay, it's the size of that interval is B minus A, whether or not you include either of the endpoints. Then he went on to say something else. The measure of a countable union of disjoint intervals is the sum of the measure of each interval. Now, the sum, and we already said when we were trying to figure out what the Lebesgue integral was, that if you had several intervals, the measure of the entire interval, namely the measure of the union of those intervals, ought to be the sum of the measure of each interval. So all he's adding here is, let's go on and go to the limit and talk about a countably infinite number of intervals, and use the same definition. Now, there's one nice thing about that, and what is it? If we take the sum of a countable set of things, each of those things is non-negative. So what happens when we take the sum of a bunch of non-negative numbers? There are only two possibilities when you take a sum of even a countable set of non-negative numbers. And what are they?
It reaches a limit, or it goes to infinity?
It goes to a limit, or it goes to infinity, yes. And Lebesgue said, well, let's say if it goes to infinity, that's a limit also. So in other words, there are only two possibilities. The sum is finite, you can find the sum, and the sum is infinite. Nothing else can happen. So that's nice. And then Lebesgue said one other thing. A bunch of mathematicians trying to deal with this did different things when they were trying to deal with very small sets. And some of them said, well, these very small sets aren't measurable. Others, and part of Lebesgue's genius was that he said, if you can take a set of points and you can put them inside another set of points, which doesn't amount to anything, then this smaller set of points should have a measure which is less than or equal to the bigger set of points. So he went on, so that says that any subset of something that has zero measure ought to also have zero measure. Now, when we look at some examples, you'll see that that's not quite as obvious as it seems. But anyway, he said that. And an even nicer way to put that is when you're talking about weird intervals, try to cover that weird set with a bunch of intervals. And if you can cover it with a bunch of intervals in different ways, and the measure of the bunch of intervals, the countable set of intervals, is you can make it arbitrarily small, then we also say that the set has measure 0. So anytime you have a set S and you can cover it with intervals which have arbitrarily small measure, namely we can make the measure of those intervals as small as we want to make them, we say bingo, S has 0 measure. Now that's going to be very nice because it lets us get rid of an awful lot of things. Because anytime we have some set which has 0 measure in this sense, when we look back at what we did with the Lebesgue integral, it says, good, forget about it. If it has 0 measure, it doesn't come into the integral at all. And that's exactly the thing we want. We'd like to get rid of all that stuff. Okay, so we're going to get rid of it. We have these sets which have measure 0. They don't amount to anything, and we're not going to worry about them. Okay, let's do an example. It's a famous example. What about the set of rationals which lie between 0 and 1? Okay, well, rational numbers are numbers where there's an integer numerator and an integer denominator. And you know, people have shown that there are numbers which are approximated by rational numbers, but they're not rational numbers. And you can take that set of rational numbers and you can order them. And the way I've ordered them here, you can't order them in terms of how big they are. You can't start with the smallest rational number, which is greater than 0, because there isn't any such thing. Whatever rational number you find which is greater than 0, I can take a half of it. That's a rational number, and that also is greater than 0, and it's smaller than your number. And if you don't like me getting the better of you, you can then take half of that and come up with a smaller number than I could find. And we can go back and forth on this as long as we want. Okay, so the way we have to order these is a little more subtle than that. And here we're going to order them in terms of first the size of the denominator and next the size of the numerator. So there's only one fraction in this interval. Oh, I screwed that up. I really wanted to look at the set of rationals in the open interval between 0 and 1 because I don't want 0 in it and I don't want 1 in it, but that's a triviality. You can put 0 and 1 in it or not. So anyway, we'll leave 0 and 1 out. So I start out with 1/2. That's the only rational number strictly between 0 and 1 with a denominator of 2. I then look at the numbers which have a denominator of 3. So I have 1/3 and 2/3. I look then at the rational numbers which have a denominator of 4. I have 1/4. I have to leave out 2/4 because that's the same as 1/2, which I've already counted. So I have 3/4. Then I go on to 1/5, 2/5, 3/5, 4/5, and so forth. Okay? And in doing this, I have actually counted what the integers are, namely namely whenever you can take a set and put it into correspondence with the integers, you're showing that it's countable. And I've even labeled what the counting is. A sub 1 is 1/2, A sub 2 is 1/3, and so forth. Now, I want to stick this set inside of a set of intervals. And that's pretty easy. I stick A sub I inside of the closed interval, which is A sub I on one side and A sub I on the other side. So I'm sticking it inside of an interval which has 0 measure. And then what I'm going to do is I'm going to add up all of those things. Whenever you add up an infinite number of things, you really have to add up a finite number of them and then look at what happens when you go to the limit. So I add up all of these zeros, and when I add up n of them, I get 0. I continue to add zeros. I continue to have 0, and the limit is 0. Okay. Now here's where the mathematicians have pulled a very clever swindle on you, because what they're saying is that infinity times 0 is 0, but they're saying it in a very precise way. Okay. But anyway, since we've said it in a very precise way, infinity times 0 here is 0, the way we've said it. Okay, but somehow that's not very satisfying. I mean, it really looks like we've cheated. So let's go on and do this in a different way. And what we're going to do now is for each of these rational numbers, we're going to put a little hat around them, a little rectangular hat around them, namely a little interval which includes A sub I, and which also goes delta over 2 that way, delta over 2 this way, and also multiplies that by my computer knew I was going to talk about computers replacing people, so it made some mistakes to get even with me. Okay, so this is delta times 2 to the minus I minus 1, and delta times 2 to the minus I minus 1. In other words, you take 1/2 and you put a pretty big interval around it. You take 1/3, you put a smaller interval around it. 2/3, you put a smaller interval around that, and so forth. Well, these intervals here are going to overlap. But anyway, the union of two overlapping open intervals is an open interval which has a smaller measure than the two of them. In other words, if you take this, the measure of this, and add it to the measure of this, the union of this and this is just this. And we don't have to be very sophisticated to see that this length is less than this length plus this length, okay? Because I've double counted things there. Okay, so anyway, when I do this, I add up the measure of all of these things, and I get delta, and I then let delta get as small as I want to, and again, I find that the measure of the rationals is 0. Now, if you don't like this, you should be very happy with yourselves, because I've struggled with this for years, and it is not intuitive. Because with these intervals I'm putting in here, no matter how small I make that interval, there's an infinite number of rational numbers which are in that interval. Okay, in other words, the thing we're trying to do is to separate the interval 0, 1 into some union of intervals which don't amount to anything, which add up, but which include all of the rational numbers. And somehow this argument is a little bit bogus, because no matter what number I look at between 0 and 1, there are rational numbers arbitrarily close to it. In other words, what's going on here is strictly a matter of which order we take limits in. And that's what makes the argument subtle. But anyway, that is a perfectly sound mathematical argument. You can't get around it. It's why people objected to what Lebesgue was doing for a long time, because it wasn't intuitive to them either. It was intuitive to Lebesgue, and finally, it's become intuitive to everyone. But not really intuitive. It's just that mathematicians have heard it so many times that they believe it. I mean, one of the problems with any society is that if you tell people things often enough, they start to believe them. And unfortunately, that's true in mathematics too. Fortunately, in mathematics, we have proofs of things so that when somebody is telling you something again and again which is false, there are always people who will look at it and say, no, that's not true. Whereas in other cases, not necessarily. Okay, there are also uncountable sets with measure 0. And for those of you who are already sort of overwhelmed by this, why don't you go to sleep for 3 minutes? It'll only take 3 minutes to talk about this. But it's kind of cute. This is, in the set I want to talk about something closely related to what people call the Cantor set. But it's a little bit simpler than that. So what I'd like to do, and this is already familiar to you, I can take numbers between 0 and 1, and I can represent them in a binary expansion. I can also represent them in a ternary expansion. I can also represent them in a decimal expansion, which is what you've been doing since you were 3 years old, or 5 years old, or whenever you started doing this. Well, ternary is simpler than decimal. So you could have done this a year before you started to deal with decimal expansions. Okay, so I want to look at all of those ternary expansions. Each real number corresponds to a ternary expansion, which is an infinite sequence of numbers, each of which are 0, 1, or 2. Okay? Now, what I'm going to do is I'm going to remove all of the sequences which contain any ones in them at all. Now, it's not immediately clear what that's going to do, but think of it this way. If I first look at the sequences, I'm going to remove all the sequences which start with 1. So the sequences which start with 1 and have anything else after them, that's really the interval that starts at 1/3 and ends at 2/3, because that's really what starting with 1 means. This is what we talked about when we talked about approximating binary numbers also, you remember. It was the way we proved the Kraft inequality. It was the same idea. Okay, the sequences which have a 1 in the second position, when we remove them, we're removing the interval from 1/9 to 2/9. We're also removing the interval from 7/9 to 8/9. We're also removing the 4/9 to 5/9 interval, but we removed that before. So we wind up with something which is now we've taken out this, we've now taken out this, and we've taken out this. So the only thing left is this, and this, and this, and this, right? And we've removed everything else. And we keep on doing this. Well, each time we remove one of these, all of the numbers when I do this n times, the first time I go through this process, I've removed 1/3 of the numbers. I'm left with 2/3 of the interval. When I remove everything that has a 1 in the second position, I'm down with 2/3 squared. When I remove everything which has a 1 in the third position, I'm down to 2/3 cubed. When I keep on doing this forever, what happens to 2/3 to the n? Well, 2/3 to the n goes to 0. Okay, in other words, I have removed an interval. I have removed a set of measure 1, and therefore I'm left with a set of measure 0. You can see this happening. I mean, you only have diddly left here, and I keep cutting away at it. So less and less gets left. But what we now have is all sequences, all infinite sequences of zeros and twos. So I'm left with all binary sequences, except instead of binary sequences with zeros and ones, I now have binary sequences with zeros and twos. How many binary sequences are there when I continue forever? Well, you know they're an uncountable number, because if I take all the numbers between 0 and 1, I represent them in binary, zeros and ones, I have an uncountable number of them. Well, because I have to have an uncountable number, because we already showed that any countable set doesn't amount to anything. Countable sets are diddly. Countable sets all just go away. So anything which gets left has to be uncountable. Again, people had to worry about this for a long time. But anyway, this gives you an uncountable set which has measure 0. Okay, so back to measurable functions. And I'm going to get off of mathematics relatively soon, but we need at least this much to figure out what's going on here. We say that a function is measurable. Before, we were only talking about sets of numbers being measurable. And we had to talk about sets of numbers being measurable because we were interested in the question of what's the set of times for which a function lies between 2 epsilon and 3 epsilon, for example. And what we've said is we can say a great deal about that, because we can not only add up a bunch of intervals, we can also add up a countable bunch of intervals, and we can also get rid of anything which is negligible. So a function is measurable if the set of t such that u of t lies between these 2 points is measurable for each interval. In other words, if no matter how I split up this interval, if no matter what slice I look at, the set of times over which the function lies in there is measurable. And that's what a measurable function is. Everybody understand what I just said? Let me try to say it once more. A function is measurable if for every 2 values, say 3 epsilon and 2 epsilon, if the set of values t for which the function lies between 2 epsilon and 3 epsilon, if that set is measurable. Okay, in other words, that's the set we were talking about before, which went from here to here, and which went from here to there. And in this case, for this very simple function, that's just a sum of 2 intervals. If I make the function wiggle a great deal more, it's the sum of a lot more intervals. So we say the function is measurable if all of those sets are measurable. And now, what I'm going to do is, when I'm trying to define this integral, I'm going to have to go to smaller and smaller intervals. Let's start out with some epsilon, 2 epsilon, 3 epsilon, and so forth. Let's look at a non-negative function. And yeah.
Maybe I missed something, but could you tell me what's the definition for a set is measurable?
What's the definition for a set is measurable? Yeah, I didn't really say, and that's good. I gave you a bunch of conditions under which a set is measurable. And if I have enough conditions for which it's measurable, then I don't have to worry about, and I've said that it is measurable under all of these conditions. And I'm saying I don't have to worry about the rest of them, because these are enough conditions to talk about everything I want to talk about.
So you define your measure now is the...
I will define my measure as all of these things. And unfortunately, you need a little bit more. And if you want to get more, you better take a course in real variables and measure theory. OK, good. OK, so if I want to now make this epsilon smaller, what I'm going to do is do it in a particular way. I'm going to start out partitioning this into intervals of size epsilon. Then I'm going to partition it into intervals of size epsilon over 2. When I partition it into intervals of size epsilon over 2, I'm adding a bunch of extra things. This thing gets added because when I'm looking at the interval between epsilon and 3 epsilon over 2, the function is in this interval here, in this, over this back. It's in this interval over this whole thing, and I'm representing it by this value down here. Now, when I have this tinier interval, I see that this function is really in this interval from here to there also, and therefore, instead of representing the function over this interval by epsilon, I'm representing it by 3 epsilon over 2. In other words, as I add these extra quantization levels, I can never lose anything, I only gain things. So I gain all of these crosshatched regions when I do this, which says that when I add up all these things in the integral, every time I decrease epsilon by 2, the integral that I've gotten, the approximation to the integral, increases. Now, what happens when you take a sum of a set of numbers which are increasing? Well, if they're increasing, the result that you get when you add them all up is increasing also, and therefore, as I go from epsilon to epsilon over 2 to epsilon over 4, and so forth, I keep climbing up. Conclusion, I either get to a finite number or I get to infinity. Only 2 possibilities. Which says that if I'm looking at non-negative functions, if I'm only looking at real functions which have non-negative values, the Lebesgue integral for a measurable function always exists if I include infinite limits as well as finite limits. Now, if you think back to what you learned about integration, and I hope you at least learned enough about it that you remember there are a lot of very nasty conditions about when integrals exist and when they don't exist. Here, that's all gone away. This is a beautifully simple statement. You take the integral of a non-negative function, if it's measurable, and there are only 2 possibilities. The integral is some finite number, or the integral is infinite. It's never undefined. It's always defined. Okay? I think that's neat. If you people don't think it's neat, well, too bad. No, I guess when I was first studying this, I didn't think it was neat either because it was too complicated. So you have an excuse. If you think about it for a while and you understand it and you don't think it's neat, then I think you have a real problem. Okay. So now, I did this. Getting too many slides out here. Ah, here we go. Here's something new. Hardly looks new. Let's look at a function now, just defined on the interval 0 to 1, and suppose that h of t is equal to 1 for each rational number, and it's 0 for each irrational number. Okay, in other words, this is a function which looks absolutely wild. It just goes up to here, and it's 1 or 0. And it's 1 at this dense set of points, which we've already said doesn't amount to anything, and it's 0